which is our last physics unit, which it's crazy that we made it here. Super excited. And so we're going to start off in concept 1 talking about the nature and some basic properties of waves. And then we'll get into more of the good stuff in the future concepts. So waves, what are they? They are a rhythmic disturbance, and they transfer energy through matter or space. So what that means is some waves can actually transfer energy through empty space. They don't have to go through particles. Other waves, they have to go through matter. They have to go through particles. And what's crazy is that so they can actually move energy without necessarily moving matter, which is one of those things that can kind of hurt your brain. So like in this picture, energy is being transferred in these ripples of water, in these waves, and matter's also moving because you can see the ripples. But that's not always the case. Sometimes energy is just transferred without the transfer of that matter, which is pretty cool if you ask me. So we can kind of put waves into two general categories of classification. We can say that waves are either electromagnetic or they are mechanical. So electromagnetic waves are waves that can transfer energy through a vacuum. So we're talking about waves that don't need any matter to travel through. They can travel through outer space. This is how light waves are. Light waves are electromagnetic waves. That's why, we can see. I like to say, I love this picture of this astronaut. We could take selfies in outer space because light waves can travel through a vacuum. Now, mechanical waves are waves that can only travel through a medium. So I remember, because mechanical starts with the M and medium starts with the M. Mechanical and medium. You have to have a medium to travel through. And a medium is just matter. So it's just the matter through which the wave is going to travel through. It can be a solid, it could be a liquid, it could be a gas. Doesn't matter, but mechanical waves have to travel through some sort of particle. And this is like sound waves and water waves. So this astronaut can take a selfie, but can't make a phone call out here in outer space because the sound can't travel through a vacuum. It would have to travel through particles. Now, we could also classify waves in terms of them being transverse or longitudinal. So transverse is where matter in the medium that the wave's traveling through is moving back and forth, at right angles, so perpendicular to the direction that the wave is traveling. And when that happens, we get this nice kind of curvy, when you're thinking wave, this is probably kind of what you're picturing. So that particle motion is perpendicular to the wave's motion. This is, electromagnetic waves tend to take on this shape. String instruments, when they vibrate, they have this type of shape. Ripples on the surface of water, not like an actual ocean wave at the beach, but like the surface of water ripples are transverse. Longitudinal waves, you may see the word compressional waves on some websites or in some textbooks. So I want you to be familiar with both. We're talking about the same thing with longitudinal and compressional. What's happening is the matter in the medium is moving back and forth in the same direction that the wave is traveling. So if the energy is traveling this way, the matter is traveling this way as well. So basically we would say that the particle motion is parallel within the same direction as the wave motion. And this is how sound waves work. Ultrasounds, if you were going to take a slinky and you can make a wave with a slinky pretty easily, I'll demonstrate that in class. Those would all be longitudinal or compressional. Now, one skill I love for my students to have is I love for y'all to interact with data and graphs and pictures. So one thing I would love that y'all need to master is looking at pictures of waves and being able to label the different parts. So looking at a transverse wave where the motion is in right angles or it's perpendicular, looking like this, there's a couple parts I want you to make note of. First is a crest. You may see peak, the word peak on some textbooks or sites, but crest and peak, same thing. We're talking about the highest points of a transverse wave. So these parts at the top, that would be our crests. And then the lowest points of a transverse wave would be called the troughs. Excuse me. So that's what we would see down here. And then this dotted line in the middle, we would call that the normal resting position of a wave. So if the wave was just to kind of calm down, it would kind of have this flat line. That's kind of like right in the middle. That's our normal resting position. In longitudinal or compressional waves, the parts are a little different because they don't look the same. This is two different pictures of the same type of wave. Hopefully that's kind of lined up. You see the darker part, and then it's more compressed here, more spaced out, a little bit more spaced out here. So that's talking about compressions and rarefactions. Compressions are where particles are pushed together. So that's what we would see kind of right here in this picture, and then right here in this picture. The bottom one's a little bit harder to see. And then a rarefaction is the part on the wave where they're spread out. So that's what we see up top here pretty easily, and then down here as well. Now, there's a couple of different ways that we can describe waves with measurements. And so we're going to kind of talk through that for the rest of this concept. And so one of those ways that we can measure waves is by their amplitude. So amplitude is referring to the amount of energy carried by a wave, but it looks different in transverse and longitudinal waves. The way that we quantify that amount of energy looks different. So in a transverse wave, where actually the amplitude is the height of the wave. So from that normal resting position to the top of a crest, or even normal resting position to the bottom of a trough, that's our amplitude. You know, if that is taller, that's going to be, if it has a greater height, it means it has more energy, it has a higher amplitude. Whereas a longitudinal wave, it's the amount of compression in the wave. So how dense is that compression? If it's super dense, that means there's a high amplitude and lots of energy. If it's less dense, it's all a little bit more spread out, then it's going to be a lower amplitude and thus a lower amount of energy. Another thing we can measure is wavelength. And this is, in an equation, is represented by the Greek symbol lambda. So that's kind of what that fancy upside down y is. And this is the distance between one point on a wave and the nearest point just like it. All right, so you pick a point on the wave and then you find the next one that looks exactly like that. That would be one wavelength. And we're going to use the unit of meters to measure it. So in a transverse wave, we're talking crest to crest or trough to trough. So here, pick the top of a crest and then the next point just like it, the next top of a crest, that's one wavelength. Or, you know, bottom of a trough to the next point just like it, the next bottom of a trough, that's one wavelength. On a longitudinal wave, we're going compression to compression or rarefaction to rarefaction. So again, compression to compression, rarefaction to rarefaction, it doesn't matter, just pick a point and then find the next one just like it, and that will give you a wavelength. All right, and two more ways, well, that's a lie, there's three, but two more on this slide we can measure waves are going to be period and frequency. So period is represented by a capital T, and it is the amount of time it takes one wavelength to pass a point. So if I want to know how long does it take this one wavelength to get past this set point, that is my period. And so that's going to be measured in seconds because it is a measurement of time. Frequency, it's represented by, I call it the fancy F, is the number of waves that pass a given point in 1 second. So it's a little bit confusing, but they're inverse of each other. And so that's how we can kind of know they're related. So frequency is measured in hertz, which is Hz. 1 hertz is the same as 1 divided by a second, or second to the -1 power, you could say, which is basically the inverse of a second. So they have this inverse relationship. If you have period, you can always find frequency. If you have frequency, you can always find period. So that's something really important to remember. They work together. So the period is always 1 divided by the frequency, and the frequency is always 1 divided by the period. And if that's kind of hurting your brain, let me know in class, because I can kind of show you with the units and with some numbers. I can kind of show this to you a little bit easier, and maybe like with actual numbers, you can understand this concept a little better. But you can also see in this picture high frequency versus low frequency. So high frequency, there's going to be more waves passing a point in a given second. They're more crunched together, whereas the low frequency, they're more spread out. So you also may be noticing then, well, then frequency and wavelength must be similar, because this high frequency has a small wavelength. This low frequency has a longer wavelength, and you would be exactly right. So frequency and wavelength also have an inverse relationship. As one goes up, the other goes down. That's what we mean by inverse. So the higher the frequency, the shorter the wavelength, as we see in this first picture. And then the lower the frequency, the longer the wavelength, as you can see in this next picture here. All right, last way, now this I mean for real, that we are going to talk about how we can measure waves is with wave speed, which will be represented by a V for velocity. So we're talking about how fast the wave travels. And we're going to measure this in meters per second. And with waves, speed is dependent on two things. It's dependent on the type of wave. Are we talking about an electromagnetic wave, a sound wave, that kind of thing. And it's also dependent on the properties of the medium that the wave is traveling through. Whether it's electromagnetic wave or not, or mechanical, the properties of the medium still matter. So here's what I mean by that. Mechanical waves, like sound. Remember, mechanical medium, they have to travel through particles. So they're going to travel faster when the particles are closer together. Because think, they're jumping from one particle to the next. So mechanical waves, like sound waves, they actually travel fastest through solids. Because, and we'll learn way more about this in our first chemistry unit on matter, but solids, the particles are much more closely packed together. Liquids, they're a little bit more spread out, and then gases, they're really spread out. So mechanical waves are going to be fastest in those solids because, again, the particles are really, really close together, so it's easy for the sound waves to jump through. Liquids, they're a little bit more spread out, but still closer than gases, which they're really spread out, so it's harder for the sound to travel through. Electromagnetic waves, like light, are pretty much the opposite. Oh, totally forgot too. Think back to thermal energy. Remember, temperature is a measure of the average kinetic energy of particles in an object. And so with kinetic energy, that's the energy in motion. So higher temperature, higher kinetic energy, so the particles are moving crazier. Sound actually also travels faster through warmer mediums because in a warmer medium, that's a higher temp, higher kinetic energy. Particles are moving more, so they're going to collide more. So each time it collides, that also makes it easier for mechanical waves like sound to travel. So warmer mediums and solids are the best for sound. Now, electromagnetic waves like light, they don't need a medium to travel through. So they are going to travel fastest in a vacuum where there's no particles inhibiting their travel whatsoever. And then next fastest would be gas and then liquid. And then they're going to be the slowest in solids because those particles are actually going to get in the way of the electromagnetic wave moving. And again, we're going to talk way more about electromagnetic waves in Concept 3. All right, so that's all of kind of the background on speed. How do we calculate it? Well, its velocity or the speed of a wave is wavelength times frequency. Remember, frequency is 1 over a second, so I can multiply those. You could also technically do wavelength divided by period, which is time, meters divided by seconds, but this is the equation we typically use. So V is for velocity or wave speed. It's measured in meters per second. That fancy upside down Y is wavelength, and that's measured in meters. And then my fancy F for frequency is measured in hertz. So an example, what is the speed of a wave with a wavelength of 2 meters and a frequency of 3 hertz? Well, I know that wavelength is 2 meters, and I know that frequency is 3 hertz, and I'm looking for speed. This is my equation, and what I'm looking for is already isolated, so I don't need to rearrange. I can just plug in and solve. So my wavelength is 2, my frequency is 3, and 2 times 3 is 6, so I get 6 meters per second. All right, let's try one that's a little bit trickier. Example number 2. A wave is traveling at a speed of 12 meters per second, and its wavelength is 3 meters. Calculate the wave's frequency and period. All right, so we know speed is 12 meters per second, and we know wavelength is 3 meters. We're looking for our fancy F and our capital T for period. Now, what's my equation I have? V equals wavelength times frequency. But I want what I'm looking for. I want frequency to be isolated. I want it by itself. So I'm going to have to divide both sides by wavelength. When I do that, those cancel out. And that gives me frequency equals V divided by wavelength. Now, I also need to find period, but remember, anytime I have frequency, I can find period and vice versa. They're just the inverse of each other. So to find period, I just have to do 1 divided by the frequency that I'm going to calculate now. So let's use that first purple equation. Frequency equals velocity over wavelength, so that's 12 divided by 3, which gives me a frequency of 4 hertz. And then to find period, I'm going to do 1 divided by the frequency, which we just found was 4, and so that gives me 0.25 seconds. Alright, next I want you to try these two on your own, so pause the video, and then when you're ready, you can check through the answers. And now we're going to practice all this in class.